Okay, in this lecture we're going to cover the section 12.5 material on related rates. So let's introduce the idea of related rates. So in several applications, there is some relationship between several quantities, which may change over time. So let's say, for instance, the relationship between the price charged for some good and the quantity supplied or demanded. So if we were to experience a change in one of these quantities, that would produce a change in the other quantity. That is, if we change the price charged for some good, then the quantity supplied or demanded might change. So in particular, the rates at which these quantities change are also related. If we change the price more rapidly, we would expect to see a more rapid change in the quantity supplied or demanded. So this concept is known as a related rate. The rates of change of two related quantities would also be related. So let's explain how these related rates applications are going to work. So in our course, we will suppose that there is some relationship between just two quantities, so we'll restrict ourselves to only two quantities interacting. And then to find the relationship between the rates of change of these quantities, we have a three-step process. So our first step is to determine an equation that relates the two variables of interest. Now, in some problems, this equation is given, and in some other problems, we may have to develop an equation from information given in the problem. Now, once we have an equation relating our two variables of interest, our second step is to differentiate both sides of this equation with respect to time. And we need to remember to use the chain rule throughout, since each of these variables is a function of time. So we're going to have composite functions, and we have to remember to use the chain rule whenever we're differentiating those composite functions. Then our third part of the process is to substitute given values that hold at a particular time of interest, and then solve for the desired rate of change. So to illustrate this concept, let's look at an example. So here we are told to find the rate of change of x with respect to time when x is equal to 1, y is equal to 2, and y is changing, or the rate of change of y with respect to time is 2, given that x and y are related by the following equation. So what we need to keep in mind throughout these problems, something that's a little tricky, it's kind of similar to implicit differentiation, is that these quantities x and y that appear in this equation are actually functions of time. So the equation that we're considering here, we could really think of as follows. So y cubed, well, we remember that y is a function of time. We might write this as y of t cubed. And that's equal to 2x cubed, but remembering that x may change over time, well, x is a function of time. So we have 2x of t to the fourth, and then plus 6 times x, but we remember that x is a function of time. So it may be helpful to rewrite your equation in this way for the first few examples that you do to remind yourself that x and y are still functions of a variable t, which usually represents time. So once we have our equation, in this case it's given to us, the equation relating our two variables x and y, our second step is to differentiate both sides with respect to time. So here, differentiating with respect to time, t, let's see what we have. So on our left-hand side of this equation, we had y of t quantity cubed. This is a composite function, so we have to use the chain rule. So taking the derivative of the outer function, we would have 3y of t squared, and then we have to multiply by the derivative of this inside function. That is the derivative of y with respect to time, or dy dt. Now that's equal to, on the right-hand side of our equation, we had 2x of t to the 4th power. So again, that's a composite function, so we're going to use the chain rule. So the derivative of our outer function would be 8x of t cubed. But again, we have to multiply by the derivative of the inner function with respect to time. That is the derivative of x with respect to time, or dx dt. And then plus 6 times, well, the derivative of x with respect to t is what we're calling dx dt. Or for simplicity, we usually don't keep writing x and y as functions of time. So to simplify the notation a little bit, I might just write this as 3y squared dy dt is equal to 8x cubed dx dt plus 6 dx dt. So this was our second step. We differentiated both sides of our equation with respect to time, t, and we were remembering to use the chain rule because x and y are both functions of time. Now in the third step of this process, we're supposed to substitute the given values that hold at a particular time of interest and then solve for our desired rate of change. So in the problem statement, we were given x is equal to 1, y is equal to 2, and the rate of change of y with respect to t, or the derivative of y with respect to t, is 2. So let's substitute those values into the equation that we just found. So we would have 3 times y squared, which would be 2 squared, or 4, times dy dt, which we were given is 2, is equal to 8 times x cubed. Now if x is 1, we have 1 cubed as 1, times dx dt, plus 6 times dx dt. So simplifying a little bit, on our left-hand side, we have 12 times 2, or 24. That's equal to 8 dx dt plus 6 dx dt is a total of 14 dx dt. And then we're supposed to solve for dx dt. That was what we were asked for. So our derivative of x with respect to time would be 24 over 14. Or simplifying, we could divide top and bottom through by 2, and we would have 12 over 7. So this would be our rate of change of x with respect to time if we know the rate of change of y with respect to time, along with the values of x and y at some particular time. So this is the idea behind a related rate problem. So this example was a little bit abstract. It's just showing how this process works in general. But let's start looking at some applications. So in our next example, we're told for the Bank of America Corporation, the relationship between revenue generated and the number of full-time employees is approximated by the following equation, where R represents revenue in billions of dollars, and N is the number of employees in thousands. So we're told at one time the company had 320,000 employees, generated $128 billion in revenue, and was adding employees at the rate of $10,000 or 10,000 employees per year. So we want to find the rate of change of revenue with respect to time. So same sort of process as in our last example. So the equation that we're given here is the following. We had 2,000 times r squared, but we're going to keep in mind that r, the revenue generated, is actually dependent on time. It's changing over time. So it's a function of t. And that was equal to n cubed, but we have to keep in mind that n, the number of employees at any given time, is a function of time. It may change. So we have the following equation, and if we want information about the rates of change of r and n with respect to time, we're going to differentiate with respect to time, t. So using the chain rule, on the left-hand side of the equation, we would have 4,000 times r of t to the first, or I might just simply write it as r to the first power. But then we have to multiply by the derivative of this inner function. That is the derivative of r with respect to time, which we denote as dr dt. And this is equal to our derivative on the right-hand side. Again, using the chain rule, we would have 3 times n of t squared, or I might simply write n squared. But then we have to multiply by the derivative of this inner function with respect to time, using the chain rule. So we would have the derivative of n with respect to time. All right. So now that we have our derivative step completed, we're supposed to substitute in the values that were given and solve for the quantity that we're interested in. So let's think about the values that were given here. So reading through the problem statement, we were told that at one time the company had 320,000 employees. Now remember that n is the number of employees measured in thousands. So 320,000 means that n is equal to 320, since we were measuring in units of the thousand. Let's see what else we're given. So we were told that they generated $128 billion in revenue. So here that gives us R. Capital R is the revenue measured in billions of dollars. So 128 billion would mean that R is equal to 128. And the last bit of information that we're given is that they were adding employees at a rate of 10,000 employees per year. So that is the rate of change of the number of employees, or the derivative of n with respect to time. We were told they were adding employees, so we're going to have a positive rate of change, and an increase in the number of employees. And the rate was 10,000 per year, but since we're measuring the number of employees in thousands, this would be 10. So taking these values and substituting into the equation that we had relating these rates, let's see what we get. So we have a 4,000 times r, which was 128, times the derivative of r with respect to time is equal to 3 times n squared. Now n was 320, so we're squaring that, and then multiplying by dn dt, which was 10. So let's see what we have here. So we're going to get on our left-hand side 4,000 times 128. Using a calculator, we can see this gives us 512,000 dr dt. Excuse that interruption. And this is equal to 3 times 10, or 30, times 320 squared, which using a calculator works out to 3,072,000. So then solving for the quantity that we're interested in, the rate of change of revenue with respect to time, well, we have our 3,072,000, and we're dividing by 512,000, which gives us a value of 6. So this is the value that we're interested in. Let's think about what this represents. This is the rate of change of revenue with respect to time. So we can say that our revenue was increasing at the time that we were given this information. We say increasing since our derivative was positive at a rate of 6, but here we were measuring R in billions of dollars, so $6 billion per unit for time. And we were told in the problem, looking back at it, we were measuring rates of change in units of time per year. So this would be per year as well. Okay. So let's consider another one. In this next example, we're told that a cancerous tumor in the shape of a sphere is undergoing radiation treatment, and the radius of the tumor is decreasing at a rate of 0.5 millimeters per week. So how fast is the volume of the tumor changing when the radius is 20 millimeters? And we're given some information in this problem. The volume of a sphere, which has a radius r, is v equals 4/3 pi r cubed. So, as with our previous examples, let's maybe write this in the following way. So we have v, the volume of the tumor, which is changing over time, so it's a function of time, is equal to 4/3 pi times r cubed. But we keep in mind that the radius of this tumor is changing over time, so it's really a function of t. So once we have our equation relating our two quantities, volume and radius of this spherical tumor, we differentiate with respect to time. So let's see what we get. So on the left-hand side, we have v of t. So the derivative of v with respect to t is what we're calling dv dt. And then on the right-hand side, we're using the chain rule to differentiate. So taking the derivative of the outer function, we take our power 3, pull it out in front with the 4/3 pi. So that gives us 4 pi times r of t squared, or I'm just going to write it as r squared now. But then we have to use the chain rule and multiply by the derivative of the inner function r with respect to time. So that's what we call dr dt, the derivative of r with respect to time. So now let's substitute the given information into this problem. So once we have this, let's look back at our problem statement and see what we're given. So here, we're told the radius of the tumor is decreasing at a rate of 0.5 millimeters per week. So that is the rate at which the radius is changing, or the derivative of r with respect to t. Now here we're told the radius is decreasing, which means that our derivative is negative. Remember, a function is decreasing if its derivative is negative on some interval. So we have a negative 0.5 millimeters per week for the rate of change of the radius with respect to time. And the question is how fast the volume is changing when the radius of the tumor is 20 millimeters. So we're also given the radius at a particular time of interest is 20 millimeters. So taking those values and substituting into the equation we had in the previous line, we have the derivative of volume with respect to time is equal to 4 pi times r, which is 20 squared, times dr dt. Now dr dt was negative 0.5. So simplifying a little bit, we have a 4 pi times 20 squared, which is 400, times a negative 0.5, or that's the same as negative 1/2. So we would have 1600 pi divided by negative 2. So that gives us negative 800 pi. And let's think about what our units would be here. So the radius was being measured in millimeters. So volume would then be cubic millimeters, or millimeters cubed. And then per, the unit of time was given in weeks in the problem. So this is per week. So in interpretation, we can say the volume of the tumor is decreasing. We would say decreasing because the derivative here is negative at a rate of 800 pi cubic millimeters per week. All right. So let's consider another one. Here we have an oil production company which is concerned about an oil slick that's forming on the surface of the water in the Gulf of Mexico. We're told the slick is roughly in the shape of a circle with area A equals pi r squared, square kilometers, where r is the radius in kilometers. And we're supposed to find the rate at which the area of the oil slick is changing at the instant when the radius is 2 kilometers and increasing at 0.3 kilometers per day. So, as with our previous examples, let's consider our equation which is relating our quantities. Here we have area, which is really changing over time, so A is a function of time, is equal to pi times r squared, but keeping in mind that r is a function of t. We have r of t squared. So to get the rate of change of one quantity with respect to time, we would differentiate with respect to time. And so let's see what we have. On the left-hand side of our equation, we're taking the derivative of area with respect to time, that is dA dt. And this is equal to, differentiating on the right-hand side using the chain rule, well, we take our power 2 and bring it out in front, so that gives us 2 pi times r of t to the first power, or I'm just going to write this as r to the first power. But then using the chain rule, we have to multiply by the derivative of this inner function r with respect to t. So that is dr dt. So now, once we have our expression relating these derivatives, let's see what we're given in the problem. So here we are given that the radius is 2 kilometers at some particular time. So r, which was measured in kilometers, is 2. And we were told that the radius is increasing at 0.3 kilometers per day. So that is the rate of change of the radius with respect to time. It is 0.3 kilometers per day. So taking that information and substituting into our equation from the previous line, we have the derivative of area with respect to t is 2 pi times r, which was 2, times the derivative of r with respect to t, which was a positive 0.3, since we were told the radius was increasing. So here we're left with 4 pi times 0.3, which would be 1.2 pi. And let's think about our unit for measurement. So here the radius was measured in kilometers, so the area would then be square kilometers, or kilometers squared, per unit of time, which in the problem was measured in days. So we could say here that the area of the slick, the oil slick, is increasing, since we had a positive value for the derivative, at a rate of 1.2 pi square kilometers per day. All right. So let's look at another one. This next example is a pretty classic problem on related rates. It's called a falling ladder problem. So here we're given a ladder which is 10 feet long, rests against a vertical wall. So if the bottom of the ladder is sliding away from the wall at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall at the moment when the bottom of the ladder is 6 feet from the wall? So in this example, we're not given the equation relating our variables of interest. We're going to have to find it. So for these types of problems, it typically helps to sketch a picture. So let's consider our problem of interest. We have some vertical wall, so it forms a 90-degree angle with the floor. And there's some 10-foot ladder resting against this wall. So we have a ladder which is 10 feet long. And we're told that the bottom of this ladder starts to slide away from the wall. So it starts sliding. Our ladder is slipping, and therefore the top of the ladder is falling downward. So the question is, if we know how fast the foot of the ladder is sliding away from the wall, can we determine how fast the top of the ladder is sliding down the wall? So the quantities that we're interested in, or the variables that we're interested in, would be the distance from the wall to the foot of our ladder, which I'm going to call x, and the distance from the top of the ladder to the floor, which I'm going to call y. And we need an equation which relates these two quantities to one another. So looking at our figure, we see that this ladder, along with the floor and the vertical wall, is forming a right triangle, whose edges are lengths x and y, and whose hypotenuse is 10. So for right triangles, we ask ourselves, well, what result would relate the lengths of the edges of those triangles? And that result would be the Pythagorean theorem. So we can say by the Pythagorean theorem, we know that the sum of the squares of the lengths of our legs, that is x squared plus y squared, must equal the hypotenuse squared. So that is 10 squared, or 100. And really, x and y are both functions of time, because our ladder is slipping. So the distance from the foot of the ladder to the wall and from the top of the ladder to the floor are changing over time. So let's rewrite our equation like this. Now we're interested in the rates at which x and y are changing over time, so we're going to differentiate with respect to time, t. So let's take a look at this. Now it's similar to our previous examples. On the left-hand side, we had x of t quantity squared. So using the chain rule to differentiate, we would have 2x of t, or just x, to the first power, and then multiplying by the derivative of the inside function, x, with respect to time, we have dx dt. Then we're adding, for our next term, we had y of t, quantity squared. So again, using the chain rule, the derivative of our outer function would be 2y to the first times the derivative of the inner function y with respect to time. And that's equal to, on our right-hand side, we had a constant 100. So the derivative of any constant is 0. So now let's see what we're given in our problem statement. So we are given the following information. We're told that the bottom of the ladder is sliding away from the wall at a rate of 2 feet per second. So that is our distance x is increasing, that is the distance between the foot of the ladder and the wall, is increasing at 2 feet per second. So that is the rate of change of x with respect to time. It's positive 10 since it was increasing. Positive 2. So let's see what else we're given. So we are also given the instant when the bottom of the ladder is 6 feet from the wall. So that would be, again, our distance x, which we're told is 6. And now we're looking for how fast the top of the ladder is sliding down the wall. So that is the rate of change of y with respect to t. So here we're given dx dt, we're given x, and we're looking for dy dt. But the problem is here we don't know what y is. It's not given in the problem. So let's think about how we could find y. If we know the value of x, then we can look back at the equation relating x and y from the Pythagorean Theorem and use that equation to solve for y. So here, if x is equal to 6, or let me maybe write it out like this. So we're given dx dt and x. The question is, what is y? So if x is equal to 6, then the Pythagorean theorem gives us x squared, which is 36 in this case, plus y squared is equal to 100. So solving for y, we have y squared is 100 minus 36, or 64. And then taking the square root of both sides, we would have y is equal to 8. Here, no positive or negative, since y represents a distance. It has to be a positive 8. So now that we have all of these values for x, y, and dx dt, let's take those and substitute into our line from our equation from our earlier line of work. So here we have 2 times x, which we were given is 6, times dx dt, which we were told is 2, plus 2 times y, which was 8, we found from the Pythagorean theorem. What is this? Okay. So we have 2 times 8, and then we're interested in finding dy dt. This is equal to 0. So let's see. On our left hand most expression, we have 4 times 6, or 24. plus 2 times 8 is 16 dy dt is equal to 0. So solving for dy dt, we could subtract 24 from both sides and then divide through by 16. And simplifying here, this would leave us with, let's see, dividing top and bottom through by 8, we would have negative 3 halves, or negative 1.5. So our interpretation here, we can say the top of the ladder is falling. So here the negative in this 1.5 means that y is decreasing. And that makes sense here since y was the distance from the top of the ladder to the floor. So as our ladder is sliding, it's falling downward and y is getting smaller. So this is falling at a rate of 1.5. And let's think about what we were measuring in here. So everything was being measured in feet. So our distance y is in feet per, what was our unit for time? In the problem, everything was being measured in seconds. So feet per second. Okay. So this last example, a little bit trickier because we weren't immediately given the equation which relates our two variables. We had to find it by sketching a picture and making use of the Pythagorean Theorem. So let's look at another one like this. So here we're told at a local clothing store, the daily demand for a certain brand of blue jeans is given by P equals 50 minus X, where P is the price in dollars and X is the quantity demanded. And the cost of purchasing these jeans at wholesale is $10 per pair, ignoring any fixed costs. And then the daily demand for this brand of jeans is currently 15 pairs and declining by 2 pairs per day. So the question is, how is the profit changing? All right. So we're interested in finding the rate at which profit is changing over time if we know how the demand is changing over time. So let's think about how we would find profit. In order to find profit, we need revenue and cost. Now what we're given in the problem is the price in terms of the quantity demanded. So in here, price is measured in dollars. So if we know the price that's being charged for these goods, then we can find our revenue function. Recall that revenue, R of X, would be found by taking the price per pair of jeans and then multiplying by the number which are sold. Let's say X. So we would have our price, which we're told is 50 minus X, times the quantity demanded, so the quantity being sold, X, which gives us 50X minus X squared. Now, we also need cost in order to find profit, so our cost, C of X, we were given is $10 per pair. So we have $10 per pair times X, the number of pair of jeans which are purchased. And so our profit, P of X, is then given by revenue minus cost. So let's see what we have. P of X is the revenue, which we found to be 50X minus X squared, minus cost, which was 10x. So simplifying, P of x is 40x minus x squared. Or keeping in mind that these quantities are really functions of time, we can think about this in the following way. Profit, which is a function of x, which depends on time, means that profit is dependent on time. And this is given by 40 times x, which changes over time, minus x squared, but keeping in mind that x changes over time. So to get the rate at which these quantities are changing over time, we would differentiate with respect to time. And on the left-hand side, we would have the derivative of profit with respect to time, which would be equal to, differentiating on our right-hand side, we would have 40 times the derivative of x with respect to time, minus, using the chain rule, we pull our power 2 out in front, so I would have 2x of t, or simply x to the first power, times the derivative of x with respect to time, the derivative of that inside function. So let's see what we are given in the problem statement. So here we are given the daily demand for this brand of jeans is currently 15 pairs, and it is declining by 2 pairs per day. So here x was the quantity demanded, so we're given the current demand, x is 15 pairs, and we're given that the demand is changing, that is the rate of change or the derivative of demand, by negative 2 pairs per day. Now, why negative? Well, we're told that the quantity demanded is declining. So decreasing means a negative value for our derivative. So taking these given values and substituting into our previous line of work, we have the derivative of profit with respect to time is equal to 40 times dx dt, which was negative 2, minus 2 times x, which is 15, times dx dt, which was negative 2. So here we have negative 2 times 40 is negative 80, and then minus a 30 times negative 2 would be 60. We're subtracting that, we're adding 60. So we're left with negative 20. And let's think about what we're measuring in here. So profit was being measured in dollars, because that was the same measure for revenue and cost. So dollars per time was measured in days. So we can say that the profit is decreasing since we had a negative value for our derivative, at a rate of $20 per day.